Good afternoon, everyone. Sorry, it was my first class, so I was having some issue with the screen sharing. I hope everyone can hear me. Am I audible?
Yes, ma'am.
Thank you. So let's start. So I am the TA of this Retrosynthesis in Organic Chemistry course. So here I will discuss some questions which will help you to understand about this course and give you confidence to attend some questions for your upcoming examinations and also for competitive exams like CSI, NET, and GATE. So let's start. So today I will discuss about the enolate formation. So what is enolate? So whenever there is a acidic hydrogen, so if we add any base into it, it will be abstracted, and due to conjugational stability to this type of adjacent carbonyl group, it will show this type of resonance. See here, one proton from this center, this carbon center, has been abstracted by this base, generating this carbanion intermediate, which undergoes conjugation with this adjacent carbonyl group and giving us this type of double bond. Now, why this is called enolate? In, the word in coming from as there is a formation of double bond, and the all is coming because there is a presence of due to this there is a formation of hydroxy group like OH group. There is a formation, so it is called enol. So let's now, the acidity of the CH bond in this compound is caused by the combination of the inductive effect of this electron withdrawing group and also by the resonance stabilization of this anion formed due to removal of this proton. Now, this minus R or this activating group, the presence of activating group, here I have shown. What is Here I have shown the order of this electron withdrawing group, which shows based on that the acidity of this proton is also varies. Now, the removal of a proton from this alpha carbon atom of a carbonyl compound with the base gives the corresponding enolate anion. Now, it is this enolate anions that are involved in many reactions of the carbonyl compounds. So, this type of enolate, if we add an electrophile in this enolate intermediate, this enolate intermediate will react with into the intermediate in this way, like the O minus will come here and it will attack to this double bonded carbon and to this this is the electrophilic center, and form this type of product. Now this methodology, this enolate methodology can be applied in case of asymmetric synthesis also, and can create a good asymmetric induction in through carbon-carbon bond formation. By due to this, for this type of chemistry, we all sometimes we use this type of chiral auxiliary group, which is get attached to the carbonyl compound and uh, induced the stereoselectivity of the approaching electrophile. Suppose here I have shown one example. Here I have shown one example where this type of this is an auxiliary group. This is called Evans auxiliary. This is an auxiliary group. It's called in the name of scientist is called Evans auxiliary. So here you can see this auxiliary group has a isopropyl group which is below the plane. So due to presence of this anchoring group, the how this reaction goes due to addition of this VLDA is a base. To addition of this base, it will form an enolate. It will form an enolate. Now this is a electrophile. This is a allyl bromide. So this carbon is electrophilic. Now in presence of this electrophile, this O minus will comes here. It will attack to this electrophilic center. Now presence of this isopropyl group will controls or denotes from where this electrophile will approach. Now you can see, if you imagine this in a 3D, I can't show but if you imagine this in a 3D, this isopropyl group, suppose this is a planar because carbonyl group is planar because it is sp2 hybridized, so this is in the plane, the carbonyl group is in the plane. Okay, suppose this is your paper and carbonyl group is on the paper. Now this isopropyl group, now after formation of this enolate, that is also a sp2 hybridized, so this is that will be also a planar system. So this enolate is also a planar. Sorry, my pen is not working today. It was creating some issue. From next week I am trying to use the pen, so it will be easier for you to understand. So this is also on the plane, this enolate. Now this isopropyl group is below the plane, so that the below of this paper is occupied by this isopropyl group. The below due to presence of this isopropyl group, due to presence of this isopropyl group is below the plane. This below part of this paper is occupied by this or hindered by this isopropyl group. So whenever the electrophile will come, that will prefer the above the plane. The electrophile will approach from the above the plane because the lower part is stereochemically hindered by this isopropyl group. So whenever this type of auxiliary group is present, in based on the stereochemistry of the auxiliary group, we denotes that from where our electrophile will approach. So formation of this lithium enolate using LDA gives the respective cis enolate, and alkylation of the reactive alkylating agents like the methyl iodide or any kind of bromide gives the alkylated product and occurs very high level of diastereoselection because it will typically comes from the above the plane because the lower plane is occupied by this auxiliary group. Now if you want to deprotect these auxiliary, that can be done by using different type of reagents like lithium hydroxide H2A2. By using this we can deprotect this auxiliary from our system. The next topic will so it is, I hope it's clear now. Now after that we will solve some questions from different type of books that will give a better idea how this reactions goes through. Before that we will discuss another topic today, that is aldol condensation. So that is, this is also similar kind of inlet formation type of reaction, because reaction goes through a enol formation type of reaction. So for in this is aldol condensation, I think most of you have heard about this name, that is aldol condensation. So an aldol condensation is a condensation reaction in organic chemistry in which two carbonyl moieties react to form a beta hydroxy aldehyde or a beta hydroxy ketone, and this is then followed by dehydration, give a conjugated enol. So what they are saying, so in case of aldol condensation, ये two carbonyl compounds, one must have a alpha hydrogen, one must have a alpha hydrogen. So two carbonyl compound and one should have one of them should always have at least one alpha hydrogen. What is alpha hydrogen? This is carbonyl system, and with respect to this carbonyl system, this is alpha position. This is our alpha position. So in this position at least one alpha hydrogen should be available. So in presence of acid or base, this alpha hydrogen gets involved and form. So the mechanism I will discuss in the next slide. So it will react with the another carbonyl moiety or aldehyde or ketone, and will form this type of, first it will form alpha hydroxy ketone, like first it will form alpha hydrox sorry beta hydroxy ketone, because this is alpha position, so that will be beta position, forms a beta hydroxy ketone, and through dehydration, as there is another alpha hydrogen available, here you have shown the two hydrogens. If there is only one alpha hydrogen, then there is no question of dehydration because there is no hydrogens are available. But if there is a two hydrogen, there is a one alpha hydrogen is available. So through elimination of water, it will form this conjugated enol. Now this type of aldol condensation can be base catalyzed, as I said, and also can be acid catalyzed. If you are taking two aldehyde with one of them having a alpha hydrogen and adding some amount of NOH in a one vessel, and in another batch you are adding an acid, both of them will give a conjugated enol or a beta hydroxy carbonyl compound. So how the, in case of base catalysis, how the reaction goes? In case of base catalysis, the base first will abstract one of the alpha hydrogen, and that goes through a conjugation, forms this type of enol moiety. As I said, this is similar to the enolate chemistry. This forms this enol moiety, and again like enolate chemistry, the O minus will come here, and through this carbon double bonded carbon, it will attack another carbonyl compound and forms, through hydrogen abstraction, it forms this beta hydroxy ketone, or here as it is aldehyde, so it will form a beta hydroxy aldehyde. This is a beta hydroxy aldehyde. beta hydroxyaldehyde, and again similar to the previous one, again through proton abstraction it will give us this conjugated enone. And how the reaction goes in case of acid catalyzed? In case of acid catalyzed system, due to addition of H plus, this oxygen has a lone pair, it will take up one of the proton, and due to that this hydrogen gets, due to this hydrogen, and as this hydrogen is acidic, sorry, one second. So this will, sorry, so this will take one of the, this will as due to, in presence of this acid, this carbonyl oxygen gets protonated and this hydrogen gets some acidity, and it will take part in this type of resonance and forming this enol, and again due to addition of another aldehyde, this enolate carbon will attack to this another aldehyde carbon and forms this type of beta hydroxy aldehyde, and through proton abstraction it will form this type of conjugated enone. Now let's solve some questions from different type of books. Here I will discuss 10 questions today. Every day I will try to solve 10 questions. If anyone have any doubt, try to solve this along with me. If you are having any doubt regarding these questions, how they are happening or something, so you can ask me now, and also you can take a time and try to practice this by yourself. Then we'll discuss that in next classes. So here I have 10 questions. I will solve 8 of them today as much as I can, and I will give 2 as a homework, so you can try by yourself. That way I will discuss in the next week on the same time, because I think for this course there will no it will be helpful, and it will give you an idea how to approach to the questions. So here is the first. So what is the, they said predict the major product formed in the following reaction. Sorry, it will be reaction. Predict the major product formed in the reaction. So what they have given this cyclopropanone ring, cyclopentanone ring with this CO2 Ame group. Now they have added this compound and with a base. NaOH is a base. NaOH is a base. So what will happen? I will give 1 minute. Just try to. You can see both of them, and options are given. Just by for your idea, just try, and then I will solve it. Which options for the first one and the second one? So let's try the first one. So here, as we said, base is added, and whenever there is a ketone with alpha hydrogen and if you add base, that will just think about, first you should check that there is a possibility of enol formation or not. So what will happen? It will form. Now there are two types of alpha hydrogen is available in this system. One is this one. One is this one. Another is this one. Now which will be abstracted? As there is not mentioned that excess base, so only one proton will be abstracted at first. So which of them will be abstracted? Of course this one. Why? Because this is more acidic. It is adjacent to two carbonyl compound. So this hydrogen is more acidic. So this hydrogen will be abstracted, forming this enolate. Now when we are adding this brominated compound, so bromine acts as a good leaving group. Bromine bromine acts as a good leaving group. Because of that, our enolates will react in the similar way like I showed previously, and tuck in this center, and bromine will be eliminated. So which will be our product? Option. Yes, Raju, you can ask. So our answer will be option B. Okay, our answer will be option B. I hope it's clear. Okay, let's go to the where we can use this. Which one? This type of reaction. Sorry, I couldn't get your questions. This type of reactions, to form a, in case of retrosynthesis, you want to make a natural product or something, a big structure. Now you have to form the structure from a small compound. So by this, here you are adding a electrophile into the center. So so if you want to prepare a structure where you want to incorporate any group or any electrophilic carbon center, or form a carbon carbon bond adjacent to the carbonyl center or the alpha center, you can apply this chemistry. So this is a simple base is abstracting one of this proton, as this proton is acidic, and this proton is involving with this proton is acidic as well as res, um, resonance stabilized. Due to this proton will take up, and the negative center will, this carbon will be negatively charged, that is it will turn into a nucleophile, and this nucleophile is reacting with the electrophile. That is a simple. This nucleophile is reacting with our electrophile, which is coming from this center. This is our electrophilic center. So our nucleophilic center is reacting with our electrophilic center. Okay, let's go to the next question. This is similar type of thing. I hope it's after solving this one, it is quite easy, because here is also alpha hydrogen, base is given, and also a brominated compound is given. Now just try. I'll give 10 seconds. Okay. So here first one proton will be abstracted and form this nucleophile. Now, as there is bromine, we know bromine is a good bromine is a good living group, and it's a better living group than chlorine. So first this one will be substituted, so it will attack here and bromine will be eliminated and form now. If we add, now there is another chlorine is also available and base is still there, so that base will abstract another proton from this, and there is another chances of alpha hydrogen is available, so that proton will abstract this alpha hydrogen and form a negative center here, and that will attack at this position and remove this chlorine center. So what will be our product? Our option C. So product will be option C. Okay. I think it's clear. Anyone has any doubt? So let's go move to our next question. So this is just try the question 3. What they are saying: predict the stereochemistry of the product formed in the following reaction. So you have to predict. So this is again the similar type of reaction. Here is also a cyclopentanone type of ring with the CO2 group. Here is also cyclopentanone. So the difference is they have mentioned the stereochemistry of the CO2 group, that is not mentioned, and there is another group present which is whose stereochemistry is also mentioned. So here just the concern was you have to draw the product. The concern was just to draw the product. The stereochemistry was not in the concern of this question, but in this case you have to show the stereochemistry of the product, the incorporating methyl group where it will be incorporated, above the plane or below the plane. As I was discussing in the when I was discussing the enolate chemistry, I was talking that whenever there is a auxiliary group and the below the plane is occupied, the electrophile will come from the above the plane. I hope you got that idea. So try to apply this in this case also. So just give it a try. I will solve it after 1 minute. Just you can try both of them, 3 and 4, because both are similar type of. Sorry, this option is incorrect. This will be here. Just give it a try. Okay, let's start. So here we have to predict the stereochemistry of the product formed in the following reaction. Now, as the base is given, so in the normal way you will just, and we know which proton is more acidic, this one or this one. Obviously this one, because this is adjacent to 2 carbonyl group. So whenever this is a enolate, this carbon center is no more a tetrahedral. This carbon center is no more tetrahedral, it becomes planar. So this bond will be also planar bond. So both the phases are available because this is a planar. This is a planar compound. So electrophile come from the above plane as well as from the below plane. Now this adjacent group, now this adjacent group is already above the plane. So from where the electrophile will come? The adjacent group is already above the plane. So electrophile, this totally this group is above the plane. So this above the plane is occupied by this group because this is a large branched compound. So the above part of this compound is already occupied by this group. So whenever the electrophile apply that appear, that try to approach from the below the plane. So the electrophile will approach from the below the plane. Here the electrophile is methyl iodide from the below the plane. So the electrophile is incoming from the below the plane. So now as the methyl group is in below the plane, so CO2 will automatically grows to the above the plane. So the correct option will be option A, because the methyl group is below the plane and the CO2 is above the plane, and that was already above the plane. So you have to understand from where the electrophile will approach. Okay, so from here you can get an idea that whenever there is an adjacent group which is controlling the stereochemistry of the complete entire molecule, if that is in above the plane, then the incoming electrophile will approach from the below the plane, and if this is already below the plane, then the incoming electrophile will approach from the above the plane. Okay, you guys can take a screenshot of these questions and try by yourself, because until you solve these questions on paper, that concept will not be clear. And for depth idea, you can follow the books like Karisenberg, Nards, and for basic Claydon and all these reactions. If you get an idea about all these terminologies and all these small reactions, that will give you an idea how to approach to a big natural product, because this to form a big compound, that is, you need some small reactions to reach to that big structure. Let's go to our next question. So predict the major product form in the following reaction. So here also they have given this lithium and ammonia, that is also act as a base and has the and they have given this electrophile, this allyl bromide is actually allyl bromide, that they have just drawn it in a different way. So how the reactions will take place, just take 10 seconds and think. So what will be the product in this case, as lithium ammonia also acts as a hydrogen donor or a electron donor, single electron donor. So lithium lithium will give a hydrate source, lithium ammonia will give a hydrate source, form this one. This looks like an enolate. Now when electrophile is added, cell goes here and attacks to that electrophile, that is this allyl bromide. and we get our desired product. Now here the question is not only the product, we have to determine the stereochemistry of the product also. Now as this is a planar, this is now a planar, so whenever it is approaching to the electrophile, it will try to keep the electrophile just in the opposite plane of this adjacent group, because whenever you are you already have something. Now you are uh, in taking something inside or keeping something adjacent to that, so you always try to keep in that way. It will suffer less steric interaction steric interaction. So that is only possible if the already present group is already in the above. Whenever something is coming, if you keep that just opposite to that one, then it will suffer less steric hindrance. So whenever this is planar, so that incoming group will always take up a opposite plane adjacent adjacent to that group. So it will take below the plane. If it takes the below the plane, the another one will be below above the plane, or both are possible here. If the upper one is in the above the plane, then the methyl will be the below the plane. So whichever options are available, that will be correct. Whichever option is available, that will be correct. So here the option A matches with this one, so correct option will be option A. Okay, let's go to our next question. So predict the synthetic equivalent. What is called synthetic equivalent? That is a terminology in case of retrosynthesis you should know. Any substrate from which you are getting the product, any substrate from which or you are getting that product, that is called synthetic equivalent. That is called synthetic equivalent. So if suppose if you have a alcohol and you are getting that from the aldehyde, so this aldehyde is the synthetic equivalent. And how you are getting that alcohol? The R minus is attacking here and you are getting that alcohol. I'm just giving an example. So here the aldehyde is the synthetic equivalent. So you have to predict the synthetic equivalent, means just before the step. What was just before the step? Before this formation of this product, what was that which is the synthetic equivalent of this get this product? Now you can see from the options here already only ketones are given. Only ketones are given. This group is not given. So you have to, so the synthetic equivalent is such that there is a ketone and after reaction like the enol formation type of reaction, you are incorporating this group. Now the question is, you have to incorporate this ethyl group selectively from the above the plane, stereoselectively or regioselectively from the above the plane, stereoselectively from the above the plane. So you should have some kind of controlling group which will restrict the approach of this electrophile from the above the plane. So that can be and any, so in case of previous reaction you can see this type of controlling group you can't remove from the system because these are inside the system. You can't eliminate this group from the system or you can eliminate this methyl from the system because they are part of your compound. They are part of your compound. But what you can just to create a chiral induction, and after that if you want to remove that group, that is called auxiliary, which I was discussing initially. So what is called auxiliary? by addition of this auxiliary you can create a chiral induction, and after that it can be removed from the system easily. So if you just imagine a chiral auxiliary here, then after removal of this you can get our this product. So, and as we discussed earlier, whenever any chiral auxiliary group has any substituent above the plane, then the incoming electrophile will come approach from the below the plane, and if the chiral auxiliary has any group below the plane, then the approaching electrophile will come from the above the plane. So here you have to imagine a chiral auxiliary which is having a group below the plane. So here this is also a chiral auxiliary, this is also auxiliary, this is also auxiliary, this is not auxiliary. This is a very small OET group that can't control the stereochemistry of the approaching electrophile. So this is first, this is not auxiliary, so this is first cut out. Now this is a auxiliary, but it has no such group inside it, so it can't control the stereochemistry of the product, so it is also eliminated. Now the confusion is between 1A and B, which will be the right option. Now you can see the approaching the incorporated ethyl group is in above the plane. The incorporated ethyl group is totally above the plane. So you have to draw your chiral auxiliary in such a way that it should incorporate in above the plane. So what will be this one? From the previous example you have got an idea that if your chiral auxiliary have a group below the plane, then the above group that approaching electrophile will come above the plane. So the correct option will be option B. Okay. Now how from this to this, how can I just for an idea, from this to this how can you go there? If you are just adding a base, if you are adding a base and this ethyl bromide, that will give us a selectively added ethyl group. Then sorry, then just to remove this chiral auxiliary, what you should use, if you add the second step, if you add lithium hydroxide, if you add lithium hydroxide, it will give us your desired product. Okay. So by this one, by this type of reaction, if you incorporate a group into, like if you have, you start with a simple acid and add this chiral auxiliary, it will form this type of structure. Then after that do this another type of reaction, a group will selectively added to the one carbon one from the above the plane, then just eliminate the auxiliary from the system and get your desired product. So this is the second one. I have also discussed another topic which is aldol condensation. So this is based on that. Just give it a try, then I will solve it. Just take 10 seconds. Let's try. So whenever OTMS means trimethylsilane. Trimethylsilane. So whenever there is F minus, silicon fluorine bond is one of the strongest bond in this world. Silicon in chemistry. Silicon fluorine bond is one of the strongest bond. So whenever there is a fluorine source, that will selectively always attack to the silicon. If there silicon is available, that will first attack to the silicon. So this fluorine instead of oxygen or any carbon center, it will first selectively attack to the silicon. So what will happen? So silicon is now pentacoordinated. So what will happen? This bond will break and this carbon center will attack to the electrophile. So here the electrophile is this aldehyde. It's aldehyde and that will open and form this as our product. Okay. So our correct option is option B. Correct option is option B. I hope it's clear. Let's go to our next question. Select the correct order of reaction required for this product formation. So to get the product, so here to get the product from here to here, what are the correct order of reaction? You know that whenever there is a bold arrow, that means this is the substrate, this is the starting material, and this is our product. So what are the correct order of reaction to get this product? Just think 5 seconds and I will answer this. If you all know about the Michael addition reaction, whenever a nucleophile is attached to the beta carbon of the alpha beta unsaturated compound, that is called Michael addition or Michael reaction. And aldol condensation we have already discussed. So that can be formed to Michael addition followed by aldol condensation. So I will show this. This is also known as this total how is this possible? So I'll just draw them, discuss it. This question was bit difficult if you don't know about this. I was trying to just mix up easy to hard. So if you add this alpha beta unsaturated ketone with base, what will happen? This proton is more acidic, so this will be abstracted, and this, and then to this nucleophilic carbon it will attack to this center. This will open, forming okay. Now in presence of base also act as a good, this alpha hydrogen is available, so it will deprotonate this alpha hydrogen, and this through this negative center it will attack to this adjacent carbonyl compound, forming this. Now again, as there is another alpha hydrogen is available, so it will eliminate water, and you get our desired product from this one. Okay, so the next reaction is combination of Michael addition followed by aldol conjugation. So the option will be option A. This is also known as Robinson annulation. This is also known as a Robinson annulation. The total, this compact version is called Robinson annulation. So whenever that anywhere is mentioned that Robinson annulation, so what will think? Robinson annulation is just a combination of Michael then aldol. It's not like if we first perform aldol then Michael, then you will not get this product. You have to perform Michael addition followed by a aldol condensation. Then you will get this Robinson annulated product, this bicyclic product. Promising. So what is the application of this reaction? If you want to get a bicyclic compound from a monocyclic compound, you can easily perform this reaction to get this bicyclic compound from a monocyclic compound. This is called Robinson annulation. So the next question is, you have to predict the product formed in this reaction. You have to predict the, similarly it is in the previous one we have a group at this position, but here we have a group at this position with the above the plane. So where the incorporating group will be placed, just give it a try, then I will solve it. Just give it a try. So this lithium aluminum hydride will give a H minus source in the like previous reaction that will attack to this beta position, and this goes here, goes here. As there is AC2O group, so it will be O minus will attack again to the acetyl group, forming OAC. Now as this is a Gilman reagent, so this gives, sorry, it will be methyl, not M. So it will give CH3 minus as kind of CH3 minus as a nucleophile, so that will attack to this place. Sorry, electrophile. There's some issue with the question. Sorry, I just gave. I just made a mistake. Why this is error? This will just reduce. So as lithium aluminum hydride is a reducing agent. It's not. I just got confused with this two question. So lithium aluminum hydride is a reducing agent. So it will reduce this carbonyl group to the hydroxy group, and after that, as AC2O is present, so the hydroxy will be acetylated. The OAC will form. Now, as we are adding this Gilman reagent, it will give a CH3 minus source. Now, as this methyl group is already above the plane, now as the methyl group is already above the plane, so the incoming methyl will always take up the opposite plane, that is the below the plane. It will come here, this double bond goes here, and OAC get eliminated. So that will always take up a place where it is below the plane. The correct option will be option C. Okay, I just got confused with the two questions. So first, lithium aluminum hydride will reduce the carbonyl compound. After that, this OH, due to presence of this Ac2O group, OH get acetylated, and again the methyl, due to in presence of Gilman's reagent, which produces a CH3 minus. This gives a CH3 minus. That CH3 minus will act as a nucleophile and attack to this carbon center, and eliminate this leaving group. And now, as it already have a group present in this compound which is above the plane, the incoming nucleophile always approach from the opposite plane, that is below the plane. So the correct option will be option C. Okay, so let's go to our next. I will solve this one. This one will be as kind of homework. You guys will try this by yourself. Then we will discuss it in the next class. Okay, Just try it by yourself, because until you solve it by, it will not be clear reaction. If you just go through again more lots of thousand and thousand of reaction, but if you can't solve it by yourself, that won't help you at all. So now here again, this lithium and ammonia is given. So what happens? In presence of lithium ammonia, it acts as a reducing agent, Bart's reduction, if you have heard about not, Bart's reduction type of reaction. In case of electron deficient ring or electron deficient double bond, we use this Bart's reduction to reduce the ring. So what will happen? In presence of this reagent 1, this ring is reduced and form this reduced pyridine, where one double bond gets reduced. Now in presence of H plus, it will take up on the proton. After that, in presence of another proton, sorry, use potential again. So as H3O plus, so water molecule is also there. So this water molecule will come and attack to this imine center and open this. Then again this OH bond comes here and open up this CN bond, forming this carbonyl group. Then this amine center gets oxidized in presence of water, like the similar way that it will take up one proton, then again water molecule will come here and it will eliminate this reaction. So it will be also transferred to this diketone type of compound. So this is our intermediate. This is our intermediate. After similar type of H plus when in presence of H3O plus, this center will also get protonated, and through elimination it will form this diketone type of ring. Now they have added base. So in presence of base, we know as there is a alpha hydrogen, alpha hydrogen, alpha hydrogen. So there is a high chance of aldol condensation. Now aldol condensation will be in such way that it forms a stable ring, because if both the carbonyl group joins, it will form a ring. So it will happen that alpha hydrogen will be abstracted, which will form a stable ring, and also the acidic one. So among this one and these two, this is more acidic because it is just connected to one carbon carbon bond, and that is two carbon carbon. Alkyl group gives a plus I effect, alkyl group gives a plus I effect, so this is more acidic. So this will get abstracted, forming this minus, that center will attack here and opens up, and through water elimination of water, it will form this product. It will form this as our product. Okay, so which option will be right one? Sorry, option B. So correct option is option B. Okay, so here it is very surprising how from a pyridine 2,2,6 dimethyl pyridine you are getting alpha beta unsaturated cyclohexanone type of compound, cyclohexanone type of compound. Okay, just through a series of reaction. So you have to know all these type of reactions so that you can get a product, because sometimes you know one reagent but you don't know others, so it is very difficult for us to get to the next step. Okay, so this is the overview of today's class, where I have tried to discuss about the enolate formation, followed by how the stereochemistry control can be possible in case of enolate formation reaction, followed by aldol condensation, and how the reaction takes place in presence of base as well as in presence of acid. Then I tried to solve some questions which I taken from different type of books. You can go through, if you haven't, I will try to share the questions, and I will try to upload this video also where you will get an idea. So here I have tried to solve these questions which are based on enolate chemistry as well as aldol chemistry. So this is the overview. If you just try to go through this topic and solve these questions by yourself, if you have any doubt you can ask me in the next class. I will try as much as I can to solve your doubts. Okay, so this one is a homework, taken as take a screenshot or a picture of this one so that you can try. Options are given, just give it a try. That will give a clear idea how to approach to your questions. Okay, so thank you. I hope I have tried to explain as much as I can. Okay, we'll meet in the next class. Thank you. Anyone has any doubt? I think it's clear. Okay, thank you so much. Have a nice day and happy Republic Day to everyone.